much of this you want me to go over?
Can you go over 2D?
Yeah, I can. So D for number 2. They're looking for T of D of X. So,
Wait, no, that's C.
oh, it is?
Yeah.
Yeah, that's fine. Do you have C okay?
Yeah.
1.08x
Yeah.
minus 1296, or how did you write it?
That's how I had it.
Okay, let's do that, because in order to get D, you need to know C. So, how much will you save on the car if you take the discount over paying the tax rather than after? So, you can do this thing purely algebraic, or you can do it conceptually. And T of D of X ends up being 1.08 of the discount taken first. So if X is the price of the car, and you wrote C, so then you would have done T of C. So it's no big deal. I don't know, I scribbled across some things that I had started writing. But if this is the price of the car, you take the discount first, that gives you an amount, and then you have to pay 108% of it. So this is discount first, then tax. So if you pay that, then you have 1.08x subtract 1296. So essentially what you're doing is you're paying the tax on the whole price, but you don't get 1200 off, you get 1296 off because you're paying $96 less for tax.
Oh.
And that's where it comes from, right there.
Because I was confused as to how to find that, but I guess that makes sense.
Yeah, let's say you did D of T of X. Okay, so then what you gotta do is you gotta take the tax thing, which is 1.08x, and then you're putting that, you're doing 1.08x, and you're putting that into the equation which has the discount, and the discount is how much? 1200. So that would look like this. You would pay the tax on the whole price of the vehicle, then take off $1,200, versus paying the tax on the whole vehicle and then taking off $1,296, because you get to take the money, the discount first. So now this tax is actually on a smaller amount. So that's where your $96 difference comes from. What else? The graph one, y is x squared minus 4. Okay, so you can make a table to graph this. You could put it on your graphing calculator to graph this. But conceptually, you know that it's x squared. We should be at this stage where we know it's simply x squared, which is a parabola opening up. And then the question is it a shift left and right? Is it a shift up and down? And when we write equations in the form y is equal to ax squared plus bx plus c, the left-right shift comes from the b value. How narrow it is comes from the a value. And the c value is the y-intercept. It is the y-intercept because when x is 0, both of these values are 0. So then we just simply have y is equal to c. So in other words, if you took a table of values and you put x is equal to 0, in this equation, whatever c is what you get for your y value. So that's going to be the vertex, that's going to be the y-intercept. So there's no left-right shift. That's the y-intercept. And the thing opens up. Now, where it crosses what? When x is 2, 2 squared minus 4 equals 0. And when x is negative 2, negative 2 squared is 4 minus 4 is 0 also. And when I graphed it, I went a little further. I said when x is equal to 1, that would be 1 subtract 4 is a negative 3, I think, is what I came up with. So this point here is 1, negative 3. And then over here, there's a negative 1, negative 3. So when I graph these, I graph the right-hand side, knowing it's going to be symmetric. I figure out where the vertex is, down here at negative 4. So I say, well, 1 goes to negative 3, 2 goes to 0. 3 is going to go to 9 minus 4, which is 5, right here. And then I go, well, 1, 2, 3 over gets me to 5, then 1, 2, 3 back gets me to negative 5. I'm sorry, gets me to 5 also, from negative 3. So negative 3, up 5. So that's how I sketch my graphs to get them symmetric. Then to come up with the inverse. The first thing we have to do is we have to figure out what the equation is. Although you could say, you know, it's got to be reflected over the y equals x line. And then you're only going to take half of the parabola. Because if you reflect the whole thing, it's going to be like this. At least that's what it is if you want a function. If you want to graph the whole equation, then you take the whole parabola and you reflect it. So, graphically speaking, this reflects up here to negative 4. It would reflect over the y equals x-axis to negative 4. And then it's going to be a parabola like this. So, but we need to know what it is algebraically. So we switch x and y. So x is equal to y squared minus 4. We add 4 to both sides. Then we have x plus 4 is equal to y squared. But we're going to take the square root of that, so we're going to take the square root of this. But when we take the square root of anything that has a variable in the radicand, you have to have a plus and a minus. That's where you get your curve above and your curve below. So the square root of x plus 4, if I have negative 4 put into here, negative 4 plus 4 is 0. That's this point. If I put, let's say, let's pick another number. If I put 5 in here, 5 plus 4 is 9, and the square root of 9 is 3. So I go out here to 5, and then I get to go up to 3, like this. If x is equal to 0, the square root is 2. 0 plus 4 is 4. So then you have a line like that. So that comes from the right-hand side of the parabola. That's the right-hand side of the parabola reflected over the x-axis, or over the y equals x line. Then you're going to have something reflected down below, because we're taking the negative square root. So you find the square root, and then you go negative. So when you have a negative 4 plus 4 is 0, and that's still going to be this point here. And then if you had, let's see, 0 put in, 0 plus 4 is 4. The square root of 4 is 4, but we're going to take, or the square root of 4 is 2, but we're going to take the negative of that, so we go down here to negative 2. So that's negative 3, this is negative 2, so it's going to come this direction. So this is a reflection of this point. And then this came all the way up to 3, so it's going to be a reflection down here to negative 3.
So did I get a point off just because I didn't show the entire parabola?
Yeah, because it said, the next question talks about whether it's a function or not.
Okay.
So if we were going to graph it as a function, the only thing that we would include would be the upper half of the parabola.
Yeah, that's what I...
So what we could say is that the domain of the entire function is when the original equation has x being 0 or greater. So only this part of the function can have an inverse. And then that becomes the top half. and then this is not included, if you're looking at a restricted domain to give you a function for the inverse. So, the multiple choices were weird. But it would be x is greater than 3, because you can't have x greater than -4. If you did, it would be taking this portion of the original equation, and that you can't have. You can only have this portion. So x is greater than 3 could be a restricted domain from here out. -4 through 3 could not be a restricted domain, because you would have the graph, the original graph, going in two directions. And x being less than 3 would not work, because it has to end at 0. You can't have negative values for the original function's input. So that was a tricky word question. For number 8, don't forget to take the fourth root of 81 as well, which is equal to 3.
So then what about 4? How do you show that?
Okay, so for 4, you had to find f of g of x and g of f of x. Yeah, this is kind of like an all-encompassing question. If you could do this one, you could do anything, I think, on the quiz. So f is x minus 7 over 3. G is 3x plus 7. So we have to show that they're inverses. And the way that we would show that they are inverses is by basically, if we put g into f, we should get x back. If we put f into g, we should have that simplify to x as well. So, finding f of g of x is taking this and putting it in the place of x. So this becomes that. And when we do that, we have 3x plus 7 minus 7. See, there's your g function. And that is all divided by 3, because all of f of x is divided by 3 when it's done. The entire numerator is. So now what we do is we work in the numerator position and simplify it. And that becomes 3x plus 0, or simply 3x. And then we have our denominator, and then 3x divided by x is going to be x.
Wait, but wouldn't you have to have 3x plus 7 in parentheses, so wouldn't you have to do that first?
Yeah, but it's not multiplication, so it doesn't matter.
Right. You could have it in parentheses if you wish.
I thought that you couldn't
Here.
actually subtract that because you
Well,
have to do that first.
all you have to do is, it's this term plus this term, subtract that term. And if you change that to the subtraction of a negative, now you can do anything. You can remove the parentheses. There's no multiplication on the outside to distribute. You just do it. And it comes out the same. So g of f of x. So now we take this and we put it in the place of just the x here. So everything there becomes just that x, and then we write the entire equation. So then that becomes 3 times this fraction. And if you want to write that fraction in parentheses, it would be a good idea. So now I think I have that going into here. So there's the 3 times the x. Now we still have to add 7. Yes? Okay, so you could go and take 3 and distribute it and call it 3x minus 21. But that would be making it more complicated than we need to. Because then you have all these fractions with big numbers that you have to simplify and work out of it. This is like 3 times a value. And this value right here, we can just simplify 3 over 3. And then that becomes x minus 7 plus 7, which just turns back into x again. So that shows that they are inverses. By inserting the function, into the inverse and the inverse into the function. So this here would work the same way. And if I took x squared minus 4 and I put it inside that radican there, I would get x squared minus 4 plus 4, which would be x squared, and the square root of x squared would be x. That's what we want. If I took this and put it into here, I would have the quantity x plus 4 squared as a square root. And that would turn it right back into x plus 4 minus 4, or x. All inverse functions, when they're put into their original parent function, will reveal x. That's how we know that they're inverse algebraically. So we have algebraic, we have graphic. We'll do more with inverses next year. Take them to another level. That's most all of it, other than the first one. If you want to go over more of it and straighten some of it out, I would suggest that you do that if you feel that you need more. These are important concepts in the future. They come up. Be happy to go over stuff. Do it after school. We're around. I have meetings some this week, but they don't start until later, so I'm available. Okay, I think the last time I saw you before doing this quiz, I gave you the first lesson of chapter 9 on exponential growth, which was a lot of review stuff. But then again, sometimes they throw a curve at us and make it so that we have a challenging question using some of these more basic ideas. Are there any that are like that we should look at? Anything from the homework? You have 14? About Taylor Willow? Put that away, please, or I'll take it and break it over the edge of the table. Not really, but... Wikipedia, huh? 1 million articles in September of 2004. In January of 2001, it had contained 617 articles. So that means it has grown an average of 18% a month since the launch date. So if f of x is equal to a b to the x, and that represents the number of articles on Wikipedia after January, x months after January. So it grew 18% a month. So how would we write that function, given those numbers? How do we write the y equals ax, I'm sorry, ab to the x? B is the growth factor. So what are we going to call the growth factor? 1.18. Yep, you got that because you have the 100% plus 18%. Okay, so what will be the a value? Do you remember where a comes from?
Would it be 1 million? Is that what it's starting?
It'd be the starting amount, but it wasn't a million. It was 617 at the very beginning. So you have 617 times 1.18 to the x, and x is number of years, or months, I'm sorry, x is the number of months. So how many articles were in September of 2004? Well, we got to figure out how many months it is. Plug that into x and then click on your calculator. And you're going to come up with a number that will be different than a million. Why might it be different than a million? Growth factor is the average, yes. So if we have points that look like this, you know, they might be off of being a perfect line. And we're taking an average. So an average is like doing, help me, a mental block, is like doing a regression. I'm trying to say recursive. It's like doing a regression on points. So they take all this data points, they lay it out, and then they do a regression, do an exponential regression. So then according to the model, how many months did it take for the number of Wikipedia articles to double from 1 million to 2 million? So what I would do with this is I'd put it in the graphing calculator and look at the number of months. Just scroll down the table, look at where it hits 2 million, and say, there we go, count that back from however many months it was at for 1 million. Can you do that? How about you two? Can you do that on the calculator? You're comfortable going there if you had to? Okay. So what else? No others? Taylor? Willow? Natalie?
14 is the only one.
Okay, good. So, do things look pretty familiar for the most part? So then negative, what am I saying, negative decay, negative growth, things getting smaller and smaller. This is going to be hopefully somewhat familiar as well. So with exponential decay, we end up having this type of a shape graph, where the big drop happens initially, and then the drop becomes less and less in quantity, but it's the same percent. So the classic is this: if you take 1 and you cut it in half in one time period, you end up with a half. If you go a second time period, you're going to go to half of that. If you go to a third time period, you're going to go to half of that, and so on and so forth. So what you might have, if this is x and this is y, is that in 0 changes you have 1 whole, and in 1 change you have a half, in 2 changes you would have a fourth, 3 changes you would have an eighth. So you have this constant here, where you're multiplying by a half, repeatedly. It's just a matter of how many times you're going to multiply by a half. So if we wrote this into y equals a b to the x form, we might say we're starting with 1. Our growth factor is now not more than 1, so it's going to be, numbers are going to be smaller and smaller and smaller. It becomes a half. Don't forget to put it in parentheses. Otherwise, it would mean just the numerator is taken to the x power. So this ends up being a half to the x. This is known as like half-life decay. So if you looked at something like, I think the carbon-14 is like the classic, although there's all kinds of radioactive isotopes in chemistry. So you're chemistry, right? Chem? No. No. Are you in chem? Okay. So what about in physical science? Did you talk about radioactive isotopes and such? And half-life? So, you know, with radioactive isotopes, we say that we start with 100% of what is present now. And then if you go a certain number of years, half of it will be gone. You go that same number of years, which is known as a half-life, another half of it is gone. So, like carbon-14 is used for dating in relatively short periods of time. It's used for dating within like the last 100,000 years, 150,000 years. If we have to date things that are older, like dinosaurs, they don't use carbon dating, they use things like uranium dating, because uranium dating involves an isotope that takes, you know, like hundreds of thousands of years for half of it to decay. And so with something like carbon-14 has a half-life of 5,730 years. So carbon-14 5,730 year half-life. If we were trying to date like a fossil from a dinosaur, because dinosaurs lived so long ago, there wouldn't be any carbon-14 left in those fossils. So what we would end up being is we'd be in a position where we wouldn't be able to date it beyond having a certain number of half-lives. But with stuff like, skeletal remains of humans and things like that, and a couple of years ago they found some skeletal remains out at one of the quarries here, I think Jack Smith's quarry. And they were like,
Skull.
what's that?
Wasn't it a skull that they found?
Maybe. And they were like, ooh, wow, is this indigenous or what is it? So they did some tests. They sent it to Fairbanks, I think, because they do carbon-14 dating. And what they did is they did something that we work with next year, but they found the amount. They found the percent of the what is considered to be the beginning amount of carbon-14. They found this percent, and then they worked backwards to figure out how many half-lives, subsequently how many years this skeleton had been dead for. Because see, we're all living right now, and what we're doing is we are putting carbon into our bodies, lots and lots of carbon. And a certain percentage of the atoms of carbon that get assimilated into our bodies are 14. You die, that means you stop assimilating more and more carbon-14, so what's there is there. And then the 14 decays. It decays because normally carbon is 12, it has 6 protons and 6 neutrons. The carbon-14 has 6 protons and 8 neutrons. So it's a crowded nucleus. And that nucleus being crowded wants to not be crowded. So protons and neutrons leave the nucleus, and it decays, it changes its atomic form from carbon to nitrogen, and it goes through some other changes. And it does that at a known rate. So an organism dies in 5,730 years. If they analyze the carbon, there would be half of the carbon-14 than what there would be in a living organism. So if we looked at X and Y as being half-lives, so X is the number of half-lives, and Y would be the fraction of carbon-14 that's in a specimen. If you have 0 half-lives, you have 1 whole. So it's like what I started writing here. If it goes through 1 half-life, which is 5,730 years, there's going to be half of the carbon-14. If you go through a second half-life, which is going to be 11,460, is that right? You're going to have a fourth. But then there's all those years in between that it's changing from a half to a fourth, and eventually to an eighth and such. And we can work with that, but we need a couple more skills before we get into it. So what they do is they write it recursively. And they're talking, what they're doing is they're talking in this example number 2 about having 100 grams of carbon-14. So if you have 100 grams of carbon-14 and you let it sit for 5,730 years, how many grams do you have left over? So without having to rewrite a whole bunch more, if you have 100 grams at start, that's right here. How much do you have after a half-life? How many grams? 50. And then how many grams will you have after 2 half-lives? 5. And after 3 half-lives? 12 and a half. So you would end up having an eighth of the original amount. We can carry that out for a long, long ways. So if we're going to write this recursively, we need to have 2 lines. We need to have a line that states the beginning amount and then what the change is. So the beginning amount, yeah, so that would be A sub 1 is equal to 100 grams. And then the actual amount to of the nth term is going to be, how do we want to write this? Well, if we write it explicitly, then we start with 100. But with this right here, we're just going to say that we're just looking at what the change is. When we write recursive, we don't care about where we start. We just say that each successive term has to be multiplied by 1/2. Yeah. So what you're going to have is you're going to have 1/2 multiplied by, ooh, how do they do this one? No, it's going to be multiplied by the term previous, A sub n minus 1. So this is 1/2 times the previous term. That's recursive. Explicitly makes a whole lot more sense. Because if we write it explicitly, that works for all terms. So then you're going to have to start with your 100 and multiply it by 1/2. And that's going to be to the nth power. In this case here, we would multiply it by the nth power, because in this sequence, we do have a 0th term because we are talking about number of half-lives, and you can have the present. So this is for all integers of n. So if you look at the explicit formula, it's basically this right here. Y equals a b to the x. Those are the most useful forms that there are. Are we out at 5 after 9? Okay. 3 minutes. I'm wondering if you guys can do these problems, or if you're going to be overly frustrated at this stage. I think you're going to be okay with most of it. Take a look at the back side. Can you read those numbers? On the bottom of the sheet. Not very well. So, first column would be x. And then the next column is f of x equals,
0.6 to the x.
yeah, 0.6 to the x. And then g of x, ooh,
Equals 5/3 over x.
5/3 to the x.
Oh, yeah.
Yeah, g of x, yeah, so actually they're written up above, that's all. Yeah, so there's, it looks like g of x has more written in between, but it doesn't. So, I think you can do these, I think you'll be fine with them. Think of the glass like, sort of like half-lives, but not half of the tinting. It's actually a greater amount of tinting. You're welcome. Oh, that's right. Keeps going, doesn't stop. What do you guys have next period?
I have my online.
Your online course?
Yeah, I'm done with it, so it's just like a
Whoa. Have a good day, Natalie.
Thanks, you too.
Yeah, all right, just wanna follow the sky down there. Catch you can. Does that scare you?
That storage or anything.
Is it recording?
And I'm gonna steal Selby's seat. Just kidding, I don't want Selby's.
I'll just sit in Dalton's seat.
Or maybe I'll steal Miranda's
No
seat.
idea. You wanna steal my seat?
Not
Come at
really.
it.
She comes sit by Selby, get this Selby wisdom.
There's Selby with
Yeah, you can share, like Phoenix was like actually
Okay.
like understanding that. See?
Oh.
It's the Selby wisdom chair. Where's my chair?
I left this chapter with you.
Take this. No, I don't want that. Okay. No, thank
You
you.
are self-taught.
Thank you, but no thank you.
Self-test.
I will try to think.
This is my turn?
And there's no eraser.
I'm not good, but
Okay. All right, thank you. I'm just writing it down, I can put it in the grade book, because I won't be able to get it in there like that.
What? Okay, no, I already knew I was going to go, but you said that you would be.
Why is it in the trash can? So do you wanna know why? Because
Lucia, I think you listed about 7 too many.
yeah. Or how many did you say? Like 9 or 9 10?
I thought you said 7.
Yeah, I'm just such an awesome. Okay, well, I'm just name you. Nobody always looks like right here.
You just did it, Lucia.
Oh, okay. Lucia, we know that exact Lucia.
You know, the second you get signature, you don't want it. No, I didn't know I did that. I have to be recommended to do that. I don't have much math with stuff.
Miles an hour.
She was here.
How are you? Good.
Yeah, who's your, that's this. Ryan, yeah, we do basketball.
Huh?
Are you gonna do that?
Probably.
Do it.
Don't fall for it? I won't fall for it then. Oh, 10.5 out of 15?
12.
Oh.
All right, buddy. If you're still here next year,
Yeah.
you want to do DDM with me?
I'm definitely gonna do DD.
Ryan, you should stay in Haines.
I wanted to get
I might.
beyond it.
Good. Because you have to be my and my buddy.
I might not then.
Dalton, are you here?
Dalton is here on top.
Ryan, can you fix your
So Ryan, Orion, did you email me this thing?
What thing?
This quiz? You must have, right?
Yeah. Oh wait, what quiz?
Is that, what is that?
Nicholas?
Wait, that's ancient history.
That's not, I don't know what this is.
Whose is this?
That thing was old. Oh.
Ryan.
Ryan, you're gonna have to be careful.
Ooh, no, this is not your writing.
No. That
This,
was
oh, this is Jada.
old.
Jada, is this your writing?
Yep.
Normally what I do is I'll write your names on them. So Rylan is here, Dalton is not. Oops, oh, this is still blank. Sorry.